Hi, in this video, we're going to go into a case study where we're going to be using multivariate analysis on some household survey data. Specifically, that survey is focusing on access to basic services, food security resilience. All right, so we're going to be using Gifi methods. All right, so a viewer of mine emailed me a data set, asked me for some help on a problem, and they're working on this project. They've got survey data and they've got different regions. I think they're in Ethiopia. They in their email they said they're in Africa, but I don't actually know. There is this word is a column in their data set which corresponds to administrative regions in Ethiopia. So I think it's in Ethiopia. Don't actually know. We haven't had a conversation. The data landed in my lap, and I want to dig into it because that's what I like to do. All right. So they've got three different cities in the data sets, and they've got uh, most of their columns of their data, all but one, are binary yes no columns, and they've got one continuous variable which corresponds to some form of distance. Now, the stakeholders want to run some multivariate analysis, so something like either principal component analysis or categorical principal component analysis or multiple correspondence analysis. All right, so we're going to run through this and kind of dig into this and see what we get. All right, so one thing I want to say about this first bit, this principal component analysis, they've got mostly binary data. And in general, we don't want to use principal component analysis on binary data. Instead, we would want to use print counts. Now, true, we should not run principal component analysis for at least what we present to our stakeholders, but it's possible that they might be presenting to stakeholders who aren't comfortable or knowledgeable or receptive to print counts or other techniques within the Gifi method range. And so we should be ready to use principal component analysis, which is not the best way to go. But if that's what my audience will accept, that's what I'm going to do. Because in data science, my goal is to convince somebody of something. So I'm ready to use that. Also, principal component analysis has a lot of tools to it, and so we can actually dig into stuff that we wouldn't be able to dig into uh, because there's just so many more tools, so many more visualization techniques that we have for PCA than we have for other techniques. And so it's using PCA is actually a really good idea for exploratory data analysis, even if I know I'm breaking a few rules by dropping some binary data into there. All right, so let's go ahead and get going. So remember, whenever I do a video, I show you all my code. So this way, if you want to repeat, you want to work on something, you want to, uh, you know, mimic what I've done, I've given you everything I can possibly give you, so you're going to be successful. So first and foremost, I'm setting it up so that I don't get blasted in the face by a ton of digits when things get printed. Also, I am trying to make sure I don't see scientific notation. If I can, I prefer just regular numbers. And I'm clearing my workspace so that I don't have any residual artifacts floating around. Now I'm going to load the data, and I've already taken a look at the data. I know what's in there. So I went ahead and set up so that we have two geographic regions, which I'm coding as characters. Then the binary data I'm having coded as integer. And then there is something with a decision in the name. And I'm going to go ahead and make the assumption that that is the result of somebody reaching a conclusion, making a decision after they look at the data. Now, I don't know that for certain, but that's what I'm going to guess. I just been corresponding with the stakeholder through email. I'm not 100% sure if that's not the best way to go. Of course, we could just change this column and modify things a little bit. Now, in this column of the data, it's coded as 5, 6, and 7, and so that's not very informative. It's there is a crosswalk back and forth. Here, I'm going to go ahead and take some other information I got from the person that emailed me, and I'm going to replace all the values in that column using this line of code here to set it up so that I have explicit names, easier to figure out. And honestly, if I had to, I could figure out what the Woreda is, which is a larger administrative district in Ethiopia than Kebele. And something I like to do, I like to have row names on my data frames. So I'm going to set up my row names to have the administrative districts and then the row number on there. So that way I can look and see, like, possibly as I look through the data, I might be able to spot a trend off of this. All right, now let's go ahead and take a look at summary statistics. All right, so we have the Woreda, the Kebele. All right, there's only 2 of these administrative districts there. We have our numeric distance here. Now, the rest of these are going to be binary variables, which correspond to yes, no inputs. And so here, one thing I want you to notice, so there's 0.4, 0.87. Now here we've got 0.99. Okay, 1.4 on the low side, but not too bad. Let's just say 0.4, approximately 0.6. Now we have more than 0.99, more than 0.99, and then 0.9. All right, so we can see that we have imbalanced data on this, and that's going to be an issue. Furthermore, and I'm going to show you this in a moment, is that these 2 columns have exactly the same values every single time. They have perfect correlation. So really, we need to throw one of them out for the purpose of the analysis. Now, whenever I look at this agree extend column, I need to remember it's perfectly correlated with that. So any conclusion that I could reach using this, I might want to go, hey, there's a heels aspect that might be in there. They could be, so any phenomena I see in the data, it might be from the agree, it might be from the heels, or it could be from both of them together. And I assume that if we had more data, these 2 columns would start differentiating more. All right, so let's go ahead and look at the correlation plots. So I'm going to be treating the binary data as numeric for the purpose of the correlations, and this will help me get a better idea of the information differences and similarities between the different columns. So here I'm computing the correlation, and I'm going to be using Pearson correlation since I'm using PCA. We're using pairwise complete observations, and the reason for this is because there are some missing values in the data in the support column. All right, so let's go ahead and run the correlation plot. I always like to use ellipses, and I like to organize my correlation plot using hierarchical clustering. Here I'm choosing Ward's D. Ward's D does a good job of trying to get equal size subgroups. And so here we see that support, distance, electricity, and loan provider are all in a group. We see that Hills Insure, I think, toilet facilities and crop insurance are forming a group. We see that drinking water is on its own, and we see what I mentioned earlier, and here's so you can visually see it. 2 columns are perfectly correlated with each other, and they are often their own group. Now we can do the same thing with single linkage. Now single linkage does a better job of detecting outliers. So here, the word outlier is not very good for this purpose. This is just showing that it has information that is not available elsewhere in the data set. So we can see that these perfectly correlated columns are in their own group. That means that this interpretation is that if I remove these columns completely, both of them, other columns are probably not going to compensate for the loss of the information value in those columns. Drink water off by itself. That means that if I was to remove drink water from the data set, then the other columns are not going to pick up that informative value and fill in what's been lost. And so here we see toilet facilities and crop insurance are together. And then we have a whole, everything else here. So Wards D tries to make sure that we minimize this one was standard deviation across the cluster. Single linkage tries to make sure that neighbors are in the same group, in the same cluster. All right, so let's go ahead and remove one of the perfectly correlated columns. And so what I'm going to do, I'm going to use this one to represent both of them. I'll keep in my mind as I look at the data that there may be a hill Z or an agricultural aspect going on when I look at it. And just to make my code a little bit easier to write, I'm going to use this vector for columns that I'm using as inputs in my analysis. Now, on this next one, I'm going to impute the missing values. Okay, I really thought about what was the best choice on this. Normally, I would impute using mean imputation on this, but then, and that would be something like 0.14. If I was to do median, then I would have a 0. I decided to go against both of those normal central tendencies because the data is so imbalanced. I mean, here it's like 0.14 or something like that for the ones. So I felt like that was imbalanced enough. There's imbalance in the rest of the data set that I wanted to kind of even things out. So I went ahead and said that a 1 for this column is either a yes or a missing value on this. It doesn't changing that much. It might, exploring things before I made the video, I don't really think it makes a meaningful difference on this particular example, but other projects it could. All right, so now let's go ahead and run principal component analysis. Now, the main reason that we're doing this would be, one, if my stakeholders were not comfortable with the more advanced techniques, I would definitely run PCA if they would accept that. Also, this is a good exploratory technique to get started with the other methods. All right, and notice that I'm centering scaling the data. That's very important for this data set because that distance data set is on a very different scale. If I run this without rescaling first, what's going to end up happening is that it's basically going to be the first principal component is basically just going to be that distance because it has so much more variance on it. And to account for the variance aspect in that higher dimensional representation of data, it's basically just going to say, hey, for all practical purposes, there's one variable contributing to the first principal component. All right, so now let's take a look at what we've got. All right, so how we interpret this. So we want to focus on, for this video, I'm only going to look at two factors at a time. All right, so what we want to do, we want to look at the largest ones first. So electricity is negative, loan provider, then distance, and I'm going by magnitude, and then support, crop insurance. Okay, and so we have crop insurance in one direction, and then the rest are getting rather small. So electricity, distance to BF, loan provider, and support are going in opposite directions. All right, so here it looks like those four are being are pointed kind of like in one direction, and then we can see that crop insurance is going in an opposite direction on this one. So let's see, distance, electricity, loan, and Distance, electricity, support, and loan. Let's take a look up here. Distance, electricity, loan, and support. We can see that these are all in the same group here. Distance, electricity, loan, and support. All right, so here, this principal component, for my interpretation, is that it's picking up this group here. And then crop insurance is going in another direction. So let's take a look at crop insurance. So negative. All right, so crop insurance, what this is picking up. So remember, crop insurance has negative correlation with this. It's not that strong. I'm actually kind of surprised by how it played out. But it's basically saying that these, and then a -1 times crop insurance, remember it's rescaled, or if we switch to yes, no values, are kind of like these are all going in a similar direction from a higher dimensional point of view. And so we're picking up like the first principal component. If I was to measure that for each individual point, these 5 kind of give us like a spectrum of these, that these are all kind of correlated together. So, all right, we've got that. Now the second principal component, or we have toilet facility. So we have toilet, we have heels, insurance, I think it's insurance, in the same direction. Then we have crop insurance, and we have opposite direction support. And so then here, it's not as clear to me what these are. I'm not familiar with the survey. I don't know much about it. I'm sure that the people who wrote the survey would be able to look at this and identify what's going on. All right, so here we can see the proportion of variance for each of our principal components. Here's the cumulative aspect. And here I would just be stopping at 2. If you don't know, stop at 2. I think it's a good rule of thumb because we can just visualize 2 at a time. If we look, we can apply a biplot to give us another representation. And so when it comes to the first principal component, the largest contributor was electricity. So I went ahead and colored the points by electricity. And so we can see on the right-hand side, we have more zeros for electricity. On the left-hand side, we have more ones. Okay. Now we see we've got our crop insurance, and we've got these 4 pointed to the left. Okay. So now let's look for the second principal component. So going up, we see electricity, heels, toilet, crop insurance in the opposite direction of support. And so these 4 are going upwards while support is going down. And maybe someone with more knowledge about the survey and the homes will be able to say, hey, what is this? What is the second principal component measuring? I can't figure it out. Now here's a scree plot. So looking at the scree plot, you could convince me that 2 or 5 would be good choices. Remember, we're trying to find when things kind of start like leveling off, where we get diminishing returns as we go from left to right. So we're looking for elbows where it flattens. And so this looks like an elbow kind of to me. Here it looks like this is a little bit flatter. So you could convince me of 5 if you want to. My opinion, if you don't know, go low. So 2, especially with a small data set. This is a small data set. All right, so now we want to run our multiple correspondence analysis. This is a homogeneity analysis. This is very simple or similar to principal component analysis, but we're allowing a wider range of the variable types. So strictly speaking, principal component analysis only uses numeric data, continuous data. Here, we are going to allow nominal data. And notice I'm specifying what the levels are. And so I'm going to go ahead and run it. So setting up the levels, saying I only want 2 dimensions. Here are the eigenvalues off of this, which connect directly to the amount of variance that's accounted for. And we're going to run through and plot all the plots. So this is from, we're using the Gifi package, and I'm just going to plot everything, throw it out there. Let's see what we get. All right, so for our joint plot, so what has happened is that we are taking the we are taking the dummy matrix of the dummy variable matrix of our categorical data. Well, it's binary, it's not that interesting, but we're also setting up dummy matrix or dummy variables for our distance also at the same time, even though it's technically a continuous variable. There's only a few distinct values, so this is okay. If I had a more complicated situation, I would probably want to consider binning the distance, but if I had more distinct values. All right, so let's see what we got. We can see that agriculture 0 is coming up top, okay, and we have heels and sure down here, which is of a 0. Kind of surprises me because heels is connected to the agriculture one. We see toilets, facility, and support. Here we've got drinking water. All right, so here that this is like showing things along a spectrum where these variables are contributing to what that spectrum is, how this is established, what's the interpretation, I don't really know. And when it comes to the first dimension, I see that I have a bunch of values over here. They're all like going one direction, and distance to BF of 1, which is the smallest value, is going in the opposite direction. So here, being close to whatever is the reference point, I don't know what BF stands for, is in contrast to having yes to electricity, yes to loan provider, yes to having support. So here is a biplot. This is completely useless, in my opinion, on this because everything's on top of each other. It's not spread out enough to be useful. Here's our scree plots, and you could convince me of 3 or 6, but I'm keeping it down to 2. Let me scroll up from now. Here are the transformations that get us from our continuous variable and our binary 2-level data to the actual values that we have. All right, so or dimensions. So the black lines indicate how things were transformed to get to the original data to the dimension. And so here we can see that there is a rescaling, so that we have the values are being stretched and compressed from the original distance to the transformed value. Here we can see that we just have a basic stair step transformation that we have different values, but we can see that these are still corresponding to lower and higher values for the yes and no's. Also, we can see that it's always going from left to right, increasing for all of my binary data. Now, the stakeholder who emailed me was interested in using knots for the splines, and I went ahead and included the multiple correspondence analysis using knots. Now, I chose to use quantiles for this. Why did I choose quantiles? Because I want to make sure I have enough data for every knot I have. And so I would rather not have a knot than have a knot without sufficient data. And there's a lot of knots in that sentence. So here I'm using quantiles. And here, ordinal, we're saying that that continuous variable is an ordinal for the purpose of the knots, and the rest are nominal variables. And so here we get our eigenvalues, we get our joint plots. Looks pretty similar to what we had before. Biplot is meaningless. Scree plots, once again, 3 and 6 look like they would work. Now here we can see that the transformation has changed in that here it ends up being the same result, but the transformation is treating things differently because of that the spline aspect. And we can see that it's a non-monotonic transformation on the distances. All right, so now let's go ahead and run categorical principal component analysis, PRINCALs. Okay, so once again, I'm going to be running principal component analysis, but with an algorithm that accepts categorical data. All right, now I have to specify where are my levels, metric for my continuous variable, and then I'm going to put nominal for the nominal values, the binary ones, and I'm going to limit to just 2 dimensions. All right, so let's just go through and do this. Now, something that's nice here is that the PRINCALs gives us our loadings, and they go ahead and they do not print smaller loading values. So notice that drink water is omitted from both these, and the agriculture one is also omitted. So how do I interpret this? Once again, it's going to be electricity and loan provider, distance to BF, then support, hey, this looks familiar, and then crop insurance going in the opposite direction. All right. Now the second component, so here I feel like this is really, this has the same interpretation as the first principal component. Now when it comes to the second principal component, toilet facilities coming up very heavily, then Heels insurance, all right. Then we have support, but going in the opposite direction. Then electricity. And, I think I'd stop right there in the interpretation. And so I don't know what these are corresponding to, but, it's maybe somebody who's more familiar with the data, more familiar with the survey would be able to, reach a conclusion. All right, so now scree plot has changed. Looks a lot more like the principal component analysis scree plot than the Hammel's scree plot. And here we can see the change. So here we can see that the distance to BF has not changed in the first principal component. There's no transformation on it. Really, there's no transformation on this anywhere except for scale. There's a rescaling here, but you can see because it's a straight line, up, relative to scaling after the whole rescaling aspect, I have like relative like same distance aspect after I've just, shrank everything. We don't have any shrinkage or stretching going on in here. And here are the object scores. So here it's plotting each individual row of data onto the plot, and everything's still on top of each other. I can't really plot anything. Now we can also run PRINCALs using knots. So we'll have splines just like I did before. Once again, I'm going to use quantiles to make sure I have enough data points at every knot. And I'm using the same levels I did before, and I'm using the same ordinal as I did before. Let's see how things change. All right, so let's go through my first principal component. I've got electricity, okay. I've got loan provider, okay. Distance to BF, okay. Then I've got negative crop insurance and then support. Feels kind of familiar. And so now let's look at the second component. We have crop insurance. All right, so this is a little bit different. So sorry, I missed this one. Toilet facilities, heels, crop insurance, support in the opposite direction, and then electricity. Okay. Now let's look at our plots. So here's our scree plots. Got a little bit of an elbow there at 7, but I would still lean towards a fewer components. Here we can see that it's taken a stair-step approach to the transformation and a monotonically increasing transformation. And here is our object score. So the most important part of this model, and I would personally use the regular Prinkhouse. I feel like that's the simplest one. You know, actually, that's not the one I want to scroll to. Here we go. This is the model that I would choose off of this data set to work with, just off of what I'm running with. We've got a mixture of data types. And so I need to be able to include nominal data. Prinkhouse can do that. Okay, we've got that. And that first component corresponds to my cluster analysis, my correlation analysis. So I've got an interpretation there. So I feel like that's that's jiving with what I've got elsewhere. So that makes me feel confident that I've got good results off of this. And so I feel like this one is the best way to go with. The knots, maybe not if you want to use those. I would prefer to not have the additional layer of complication on my model unless I knew there was a good reason to do it. It's a small data set, so that's further justification of a simpler model. All right, well, that's all I've got for you. Life is short. Do math.